multi-billion-dollar resource waiting to be recovered. Instead of being discarded, each aircraft enters a tightly controlled industrial process, where every component is carefully disassembled, sorted, and processed to recover valuable materials. From a complex machine made up of millions of parts, it is gradually transformed into a stream of clean, reusable materials that deliver significant economic value to the manufacturing industry. In this documentary, join the Factorin as we step inside massive processing lines and explore how humans play with a giant mechanical system, where each aircraft is taken apart, processed, and reborn in ways rarely seen by the public. Contrary to common belief, aircraft are not immediately destroyed once they are taken out of service. Instead, they are processed in stages, with each component assigned a different value and handling method. For this reason, the entire recycling process must follow a strictly controlled sequence from the very first steps. The process begins at aircraft storage facilities, where retired planes are kept in dry environments to minimize corrosion. When it is time for processing, the aircraft is towed into the recycling area using specialized aviation towing equipment. At this stage, technicians carry out a full structural inspection. Access panels are opened to examine the internal sections of the aircraft, with particular attention given to critical components such as the airframe structure. Based on these assessments, engineering teams develop a detailed disassembly plan for each individual part. Before proceeding to the next stages, all onboard systems must be fully deactivated. Technicians disconnect the main power supply, as well as all backup power sources, to ensure that no electrical current remains within the system. Any residual charge stored in capacitors is also discharged to eliminate the risk of electric shock during handling. This is a mandatory safety step in all heavy industrial processes. Once completed, the aircraft no longer functions as an integrated system, but is reduced to a large metallic structure ready for further processing. Before any disassembly can begin, the very first step is to remove and collect all fluids contained inside the aircraft. Large hoses are connected directly to the fuel tanks located within the wings and the fuselage. Under the suction force generated by industrial pumps, jet fuel is extracted and transferred into sealed storage tanks for later reuse. The entire operation is carried out within a closed system, equipped with sensors that continuously monitor flow rates to prevent overflow or leakage at any point during the process. Once the fuel has been removed, the hydraulic system is handled next. Discharge valves are opened in a controlled sequence to gradually release the pressure inside the pipelines. This step is critical, whereas hydraulic systems can retain significant internal pressure even after the aircraft is no longer in operation. When the pressure has been reduced to a safe level, the hydraulic fluid is extracted, ensuring that no residual force remains trapped within the system. This stage can be understood as a complete internal clearing process of the aircraft. If any fuel residue or internal pressure is left behind, even a small spark could trigger a serious and potentially dangerous incident. Only when the aircraft is completely dry, free of fuel, free of pressure, and free of any hazardous materials, can the next stages of disassembly and metal cutting be carried out safely and under controlled conditions. Once the aircraft has been fully secured, the technical team begins removing the high-value components. The engines are typically the first to be taken off. Large structural bolts are loosened using specialized tools, while a crane supports the full weight of the engine to prevent any misalignment or sudden drop. As the final connections are released, the engine is carefully lowered and placed onto a transport stand. It is then sent for inspection and refurbishment, with the potential to be reused in other aircraft or adapted for industrial equipment and machinery. Next, the landing gear is removed. This is one of the heaviest and most structurally robust components of the aircraft, requiring hydraulic jacks to stabilize the structure before the retaining pins are extracted. At the same time, watch your electronic systems, including navigation units, flight computers, and control modules, are dismantled piece by piece. All removed components undergo an initial inspection, are tagged for identification, and transported into storage facilities. In many cases, the engines alone can represent the majority of the aircraft's remaining value. This stage is critical for preserving recoverable assets before the aircraft proceeds to full dismantling. Before structural cutting begins, the entire interior of the aircraft is completely dismantled. Technicians systematically remove components such as passenger seats, overhead luggage compartments, interior panels, electrical wiring systems, and insulation materials. These materials cannot be processed together with metals in the downstream shredding stage, so they are separated from the very beginning. The dismantling process is carried out section by section, starting from the passenger cabin and moving gradually into technical compartments. Each internal layer is stripped away, exposing the aircraft's primary metal frame. By the end of this stage, the interior space is almost entirely empty, leaving only the load-bearing structure in place, ready for further processing. Once the interior has been fully cleared, the structural cutting phase begins. Excavators equipped with hydraulic shears are positioned around the aircraft, gripping the fuselage firmly and performing controlled cutting cycles. The shear blades press through the aluminum skin and internal structural frames in repeated strokes, ensuring a stable and controlled operation. The wings require a more complex approach due to their thickness and load-bearing design. The hydraulic shears are positioned at the wing root, where multiple cutting cycles are applied to penetrate the main structural spars. After separation, large sections such as the wings, tail, and fuselage are pulled away and placed into individual blocks. At this stage, the aircraft no longer retains its original form and has been broken down into manageable sections, ready to be transferred to the next stage of shredding and material processing. After the fuselage, wings, and other large sections of the aircraft have been separated, the initial stage of size reduction begins directly during dismantling. Excavators equipped with grapples or hydraulic shears do not only cut but also compress and fracture large metal structures into smaller pieces. As the applied force increases, aluminum panels and internal frames begin to bend, crack, and break apart into more manageable fragments. These pieces are then picked up and loaded onto trucks for transport to recycling facilities. At the recycling plant, the material is not processed immediately, but is instead fed into large-scale industrial shredding systems, typically heavy-duty shredders. During operation, rotating shafts fitted with hardened steel teeth grip, tear, and break down the metal into significantly smaller fragments than before. The entire process runs continuously, with material entering from one end and exiting in a reduced form through the discharge outlet. After passing through the shredder, the mixed material is conveyed along sorting lines. A high-power magnet positioned above the conveyor extracts ferrous metals from the stream. The remaining material then passes through an eddy current separation system, which repels and separates aluminum from the rest. Additional sensors are used to identify and sort other metals such as copper or titanium. Non-metallic materials are also removed and directed to separate processing streams. The sorted steel scrap is not processed immediately on site, but is instead loaded onto specialized transport trucks and moved to the melting area. At this stage, each truck is directed into the charging zone, where large-scale industrial crane systems take over the operation. Massive grapple buckets are lowered down, firmly gripping bundles of scrap steel, weighing several tons, then lifting them off the ground and moving steadily toward the furnace opening. Once positioned, the crane rotates precisely and releases the entire load into an electric arc furnace that has already been opened. The impact of metal colliding with metal produces a loud resonant sound as the scrap falls inside, forming layered piles within the furnace chamber. This is not a single action but a repeated cycle, ensuring that the furnace is charged with the required volume of material for each melting batch. Every movement is carefully controlled to prevent overloading or uneven distribution inside the furnace, as either condition could directly affect melting efficiency in the next stage. When the furnace reaches its target capacity, the system transitions into the heating phase, where electrical energy will be converted into extremely high thermal energy, initiating the transformation of solid steel into molten metal. Cranes lift individual batches of steel scrap and release them into the electric arc furnace. Once the furnace is closed, the electrodes are lowered close to the surface of the metal and begin delivering a high-intensity electric current, generating an arc with extremely high thermal energy. Temperatures can reach up to 3,600 degrees Fahrenheit, allowing the steel to heat rapidly. At first, the surface of the metal turns red, then gradually softens and begins to melt. As the temperature continues to rise, the entire solid mass transitions into a fully liquid state. Throughout this process, additional material is continuously charged into the furnace to maintain a consistent volume of molten metal. Once the steel is completely melted, the refining phase begins. Lime and other fluxing agents are added to bind with impurities. These impurities rise to the surface, forming a layer of slag. The slag is then removed from the molten metal using specialized equipment. Sensors continuously monitor both temperature and chemical composition to ensure precise control. When the required specifications are reached, the molten steel becomes uniform and ready for the next stage of forming. From irregular, solid fragments at the beginning, the material has now been transformed into a clean, homogeneous mass of molten steel, ready for casting. Immediately after refining, the molten steel is not held inside the furnace for long, but is poured out through a guided tapping system. The stream of molten metal flows continuously into casting molds that are cooled by circulating water. As the molten steel comes into contact with the mold, the outer layer begins to solidify first, forming a hardened shell around the material. Inside, the metal remains in a liquid state and continues to move forward along a series of rollers. Throughout this process, the steel is simultaneously transported and gradually cooled, allowing the entire mass to solidify evenly. The continuous stream of steel is then drawn out into long, semi-finished forms, known as billets or slabs, which can extend for dozens of feet. Square billets are typically used for construction-grade steel, while flat slabs are produced for rolling into sheets or coils. Once the desired length is reached, an automated cutting system divides the continuous material into individual sections. Immediately after leaving the casting area, the steel billets remain at extremely high temperatures and are transferred directly to the hot rolling mill. Here, each billet is fed between continuously rotating rollers. As it passes through each pair, the steel is compressed and elongated along the direction of movement. This process takes place in multiple successive stages. At each stage, the gap between the rollers is gradually reduced, causing the steel to become thinner and longer after every pass. The high temperature keeps the metal ductile, allowing it to deform without cracking or breaking. Throughout the operation, the billet moves continuously through multiple rolling stands. Sensors monitor thickness and speed in real time to ensure the material meets the required specifications. If any deviation is detected, the roller gap is adjusted immediately. By the end of the rolling line, the steel is formed into uniform sheets or long coils. At the final stage, glowing red coils are collected and transferred to the cooling and quality inspection process. After leaving the casting area or rolling mill, the steel remains at extremely high temperatures and has not yet stabilized internally. It is immediately passed through high-pressure water sprays, where fine mist covers the surface to rapidly reduce heat without causing thermal shock. In some facilities, air cooling is also used, with large industrial fans gradually lowering the temperature of the inner core. This controlled cooling ensures heat dissipates evenly, preventing cracking or distortion. Once stabilized, the steel moves to the inspection stage. Samples from each batch are analyzed using spectrometers to verify chemical composition, while mechanical tests measure tensile strength and hardness. If any deviation is found, the material is separated and may be returned for reprocessing. Finally, the steel is cut into standardized lengths, ready for use in construction and manufacturing. After meeting quality standards and being cut to size, the metal sections are labeled for identification. Information such as the type of metal and the production batch is clearly recorded to ensure traceability and efficient management. The materials are then stacked onto pallets or loaded into containers for transportation to manufacturing facilities. At these plants, the bars and metal blocks are used to produce a wide range of products, including automobiles, industrial machinery, and construction materials. In some cases, a portion of the recycled metal may even find its way back into the aerospace industry. This demonstrates that an aircraft does not truly disappear at the end of its service life. Instead, it is transformed into new forms and continues to be used in an entirely different life cycle. From a machine that once flew thousands of hours in the sky, an aircraft does not disappear at the end of its life cycle. It is dismantled, cut apart, shredded, melted, and reintroduced as entirely new materials. Each stage in this process is not simply waste handling, but a reconstruction of value. The metal is cleaned, controlled, and returned to production with consistent quality, ready to become part of new products. What is remarkable is that the life cycle